Welcome to this video overview of Maya Live. We at Alias Wavefront realize that it is essential to provide any information that will help you understand how to get the best possible results from Maya Live in the shortest possible time. This video is intended to illustrate the use of Maya Live in a recommended workflow that will allow you to achieve results faster and easier. Keep in mind that all projects vary in their complexity, but we feel that this example will give you a much-needed kickstart to becoming more productive with Maya Live. In order to illustrate Maya Live's ability to merge computer-generated imagery with live-action footage, this video will use a small commercial project produced in-house at Alias Wavefront. This piece is for a fictitious laundry detergent called Stainx. The commercial is an effective way of demonstrating the power of Maya's character animation tools and integrated advanced modules like Maya Live. The final composite was layered together using Composer 5.0.
How'd you get your clothes so sparkly fresh?
It's this new extra strength Stainx.
Extra strength?
Yeah! It's even tough on Harry's smoke stains, and this built-in fabric softener doesn't irritate his delicate exoskeleton.
My Stanley can use some of that.
Before beginning the process of extracting the 3D information from the scene, it is necessary to review the footage for tracking. Maya Live allows for match moving a wide range of shots. The complexity and style of a shot dictates the approach you'll take for the solution and the degree of accuracy you'll require. Begin by setting up the shot. To track features in the image sequence, we need to import the images onto an image plane that is attached to a camera. This camera will receive the solved motion curves. Maya Live 1.0 is designed to work with any kind of film. However, video can present certain problems which should be planned for, such as interlacing, video noise, and image degradation from film to video conversion. These can make tracking harder and affect the quality of the camera match move. Images are imported onto the image plane simply by using Maya Live's file browser to select the sequence of live-action frames that have, in this example, been scanned digitally from the film footage. Selecting the camera and looking through it will allow the user to view the image sequence as it will appear in the final integrated scene. Any one of the predefined film backs can be selected for the effective sizing of the image plane to the camera and more accurately reflect the relationship between the 3D scene and the original footage. The timeline can now be scrubbed to view the entire live-action sequence through Maya Live's shot camera. Image proxies allow for the use of lower resolution versions of the sequence to be viewed during the interactive display. Be aware that if film-sourced material will be used for video output, considerations need to be made for the difference in frame rates. If a straight frame conversion of film to video is performed, then no problem should arise, except faster playback speeds. If the footage is stretched to video rate, then problems with tracking due to image degradation. As always, planning is essential before starting. It is recommended to work at 24 frames per second and then convert the entire edited program to 30 frames per second upon completion. To begin extracting the camera information from the live-action sequence, certain points on the image will be tracked using Maya Live's Track task. The Track task contains two views and a panel. The large view on the left is the shot camera, the view through the camera's lens. The top view on the right is the point-centered view, a close-up view of the selected track point. The bottom panel on the right is the track point summary, a visual analysis of all the tracked points. To create a track point, simply click the Create New Track Box button in the Track Task panel. Clicking the Track Box tool button will allow you to position the track point anywhere in the image. Positioning the track box can be done from either the shot camera or the point-centered camera. The shot camera view is used here to place the track box in the general area of the pixels to be tracked. In this case, one of the flowers in the foreground. The point-centered view automatically zooms to the selected point, allowing for more precise positioning and resizing. Track boxes are made up of an inner boundary, which marks the target, and an outer boundary, which marks the search range. The target can be resized to better match the search pattern, and the search area can be resized to better define the region in which to search for that target. It is recommended that track points be named descriptively to allow for easier identification and organization from the track point list. Clicking the Start Track button will begin the tracking process for the current point. The tracking process generates the information necessary for the solver to produce a camera solution. A progress dialog appears when the track begins. The dialog contains a view of the point as it is tracking and a progress bar that indicates % complete. A movie file is automatically generated and the movie player is launched at the completion of the track. The movie is useful for viewing a real-time sequence of the tracked point's motion, as well as allowing for thorough evaluation of the track by scrubbing through the sequence. The accuracy of the track point can also be further investigated in the track point summary panel, a graphical representation of the track point's quality and validity over time. The bar graph next to the name of the tracked point provides a visual display of the success of the track. Green areas on the graph indicate successful results, where the track error is below the error threshold. Yellow indicates degradation in track quality, and red would indicate tracking failure, where the track error has passed the error threshold. In most cases, the track accuracy for a point will decline over time as the track box gradually drifts, or if the background changes with the camera move. This error can be compensated for by repositioning the track box at the frame where the error needs correcting. In this example, the position of the track box is adjusted in the last frame of the sequence. The target size should closely fit the boundary of the point, including some of the background to define its edge, but not too much. The background changing within the target should be avoided, as well as any highlights on the feature being tracked, as the location of a highlight can change as the camera moves and cause the track point to fail. Utilizing the options to direct a track can significantly improve the accuracy of a previous track. Here the tracking is set to backward, and the tracker is instructed to stop tracking once it reaches a frame that was better correlated in the previous pass. The new movie of the tracked point can now be viewed to evaluate accuracy, and the track point summary will reflect any improvement in the quality of the track. The track point summary panel also provides tools to manage the validity of the track points throughout the scene. A point is considered valid when it is in the camera's view, but not all features are visible throughout the entire sequence. Here, a new track point is added on the watering can in the background of the image that will become obscured by the fence in the foreground. The target and search ranges are first adjusted to identify the area to be tracked. Identifying when points change from valid to invalid is very important, since it prevents the solver from incorporating undesirable track motion into a solution. Only valid data is relevant to the solver. Any irrelevant data will cause the solver to return inaccurate results. Tracking this point in the background will provide the solver with more information about the depth of the scene during the frames that the watering can is in view. The validity for this point will be turned off at the frame where the point disappears. The automatic point blast created will allow for closer inspection and identification of the exact frame that the point on the watering can is obstructed. When the frame has been identified, the track point summary can be used to inspect the validity of the tracked point. The validity for a point is indicated by the solid blue bar below its quality graph. Each track point can have different frame ranges specifying when it is valid and invalid, and points can sometimes travel in and out of view throughout the length of the shot. When a feature is visible, the track point should be marked valid. To mark the track point invalid, the frame indicator is positioned on the desired frame and the valid checkbox is clicked in the track task panel. The blue bar in the track point summary will now overlap only the section of the quality graph that is valid for the solver. When a track point is invalid, it will be drawn as a dashed outline for the duration of those frames. In this example, the point will remain invalid for the duration of the sequence. Certain criteria need to be met before a scene is ready to solve. A sufficient number of points must be tracked before a scene is ready to solve. The exact number is difficult to specify since it depends on camera motion, quality of points, and the amount of survey data. At a minimum, the solver needs 4 of the points to be visible on any given frame. Adding good quality tracked points will generally improve the accuracy of the solution, and these points can be added after a rough solution is found. For this sequence, 10 points in total were initially tracked, and 3 more were added for refinement. The track point summary provides a built-in ready-to-solve indicator at the bottom of the panel. The ready-to-solve bar displays red until there are enough valid track points for a solve. When there are enough valid points with an acceptable accuracy level, it changes to green. When solving for a camera move, the solver takes the tracked point data and calculates the location for each point in 3D space. It then calculates a solution for the camera move and allows for playback. MyAlive provides 2 methods for solving: comprehensive and root frame. The comprehensive solve is a one-step process that calculates a solution based on information it takes from every frame in the sequence. Because this method makes several passes, looking at every frame before returning a solution, it is more time-consuming and less iterative than the root frame solver. The root frame solver, the method used in this example and the method recommended in this video, uses a different algorithm from the comprehensive solve. The root frame solve bases its solution on the information in a set of frames that it selects from the sequence, or root frames. The root frames encapsulate the motion of the shot. The number of root frames the solver will select for the shot can be specified, and if desired, the particular frames that will be used as root frames can be specified by the user. There are two possible approaches for reaching a solution with the root frame solve. The easiest is to select the Solve button, which will let the root frame solver automatically generate the solution. The other approach is to interactively go through the root frame solve process one step at a time. Before solving, adding survey constraints to the scene may increase the accuracy of a solution and help register the solution. These constraints allow you to affect the focal length, scale, and relationships between objects in a scene. A plane constraint allows you to constrain a point or group of points to a plane. This is useful for establishing a ground plane or in making a group of points coplanar. In this scene, two plane constraints were used. The initial plane constraint, being created here, will represent the plane on the front surface of the fence. First, the position of the NURBS plane is adjusted on the modeling grid to align with the desired orientation of the fence. Then the track points that will specify the plane are selected from the point list. Any number of points can specify a plane constraint. In this example, 3 points are selected. The constraint is then created and named appropriately. The second plane constraint used in the scene will be created in the same way. It will represent the ground plane in the shot, so the position of the corresponding NURBS plane will not need to be adjusted. Only 2 track points in the scene will be used to describe this constraint. One of the points, on the bottom corner of the fence post, will end up being specified in both of the plane constraints. A different kind of constraint, a distance constraint, will be created as well. Distance constraints allow the user to specify the distance between 2 points in the scene. Here, 2 points on the fence are selected and their distance is entered. This method is useful if measurements were taken on the set when the footage was shot. To obtain an initial solution, clicking Start launches the solver. The solver returns with a camera position and 3D points for the root frames. The information contained in this solution is called the guess, as shown in the solution status box. The guess has a number associated with it, which is the overall quality reached in this pass. This particular value of 4.256 could be considered a good result. Keys are automatically set for the camera's position at each of the root frames. The shot camera's motion curves can be seen here in the Graph Editor section of the Solve task panel layout. The keys can be inspected interactively by using the Next Key button in the playback controls. Reviewing the results in this manner will allow the user to inspect the accuracy of the placement of the 3D locator points that correspond to each track point in the shot. If, after inspection, the result from the initial guess is unsatisfactory, the Continue button can be used to have the solver consider more solutions. For this example, the results are acceptable enough to forego the request for another solution. Selecting the Refine function will give the solver an opportunity to improve on the current solution without considering others. This is helpful in allowing the solver to focus on making the current solution more accurate. If the overall quality returned by the refinement phase matches the previous quality value on the solution, the Finish button is used to apply the root frame solution to all frames in the scene instead of just on the root frames. The Finish operation returns an overall quality value and creates keyframes for the camera at every frame in the animation, displayed as red tick marks in the timeline below. These results can now be analyzed over time by scrubbing throughout the animation to reveal any inconsistencies in the motion of the shot camera. 3D geometry can also be added at any time and positioned to aid in the inspection of the results. Here, the Layer Editor is used to display the CGI fence that will be used in the scene. The point snapping function is then used to lock the corner of the fence geometry to one of the 3D locators created by MyAlive. The fence is then scaled and positioned relative to the background image on the image plane for that frame. Geometry can also be parented to the locators during the MyAlive session. A play blast generated from the shot camera will allow for more interactive inspection of the motion. In this example, it becomes more obvious that the solution shifts orientation abruptly in the middle of the sequence. This shift corresponds precisely to the frame at which the track point on the watering can in the background has been keyframed invalid. Adding more track points to the background of the image, points whose validity overlap frames where the watering can is invalid, will help to give the solver more depth information about the scene. Here, 2 additional points have been tracked in the background of the scene. The point on the corner of the chair is visible throughout the entire length of the shot. The peak of the roof on the building in the far background has been keyframed to be valid beginning at frame 127. Incorporating these new track points into the solution is easily accomplished by restarting the solver from the initial solution. First, the initial solution is selected and the Start button is pressed. The Start operation will now recalculate new root frames accounting for the newly tracked points. Using this step-by-step method of the root frame solver will allow the user to fine-tune the results, incorporating any changes that may affect the final solution. After a few minutes, it will generate a new guess and overall quality that can again be evaluated using the methods described earlier. Here, the finish phase has also been performed on this solution, returning an overall quality of 4.773. Because the geometry of the fence has been parented to the locator on the corner of the fence in the live action, repositioning the geometry to match the new solution is unnecessary. Positioning and orienting the solution within the world, however, can be accomplished by incorporating one of the track points into the registration process. In this example, a new survey constraint will be added, using the track point on the bottom of the fence. A point constraint allows the user to specify absolute locations for points in the scene. The point is selected and the desired position for that point is entered. In this example, the point will be placed at the world origin. In some cases, the point could be tagged registration only, which would tell the solver to ignore the point when calculating its solutions, but include it in the evaluation of the solution's position in world space. Here, after clicking the Register button, the solution has been relocated so that the point at the corner of the fence post has been placed at the global origin. This example of a play blast illustrates the results achieved with Maya Live thus far for this scene. Sometimes, certain hardware display inadequacies, such as general image jittering seen here during playback, make it difficult to evaluate Maya Live's success. It is recommended that a sequence of frames be rendered using Maya's software renderer. These images and their matte information can then be composited using Composer or other compositing systems and recorded onto a Zappit system or other digital disc recorder for more accurate viewing of the results. At any time during the process of solving a scene, any one of the solutions that Maya Live has calculated can be exported by clicking the Export button in the Solve Task panel. In addition to the shot camera and all of its associated motion and image plane, all of the 3D locators in the scene, as well as any selected geometry, will be exported as a Maya scene file. This function is useful for sharing Maya Live generated scenes with other animators in the production environment who may not have the ability to access a Maya Live license. These scenes can also be rendered with versions of Maya that cannot access a Maya Live license.
Hey, Edna, how'd you get your clothes so sparkly fresh?
It's this new extra strength Stainer-X.
Extra strength?
Yeah! It's even tough on Harry Smokestains, and this built-in fabric softener doesn't irritate his delicate exoskeleton.
My Stanley can use some of that.
We hope this video overview of an actual Maya Live workflow will enable you to achieve results with Maya Live much faster and easier. This video, as well as the frequently asked questions document included with it, are intended to supply you with the information necessary to understand how Maya Live can effectively integrate CGI elements into live action scenes.